Okay, it's about 2 minutes after, so we're going to go ahead and get started because I know we have a lot of information to cover here in the next 58 minutes. So just to introduce myself, my name is Dave Eckroad. I'm the director of the IDEA StatiCa US office. Along with me is Andrea Castello. She's one of our product engineers here in the US, and she's going to be doing the primary portion of the presentation today. And the topic today is going to be something interesting for basically it's our member application, which can be used to design some critical members. So if you have buckling requirements or lateral torsional requirements on members, this is what a member could really be used for. So it's not necessarily a everyday tool. It's more for special type of member designs. And the nice thing is that it does allow you to take into consideration the end connections of the member. And Andrea will kind of walk you through all of that. So why don't we go ahead to the next slide? Just a reminder, any questions you have, feel free to use the question panel in the main control panel of GoToWebinar. I'm sure most of you have probably been familiar with that. One other thing to note is that we have put the handout in the handouts portion, so you can actually download the handout and kind of either follow along or kind of take notes on it as well during this presentation. So next slide. So just looking at an agenda. So Andre will first kind of do an introduction of what IDEA member is, which is, and really member is not necessarily a separate product at this point. It's included when you have a IDEA StatiCa steel license, and it can be used for steel and coming soon for concrete as well. She will then go over workflows, kind of using some other structural applications, talk about how to evaluate the results, and then finally, depending on timing, we will do some Q&A. So with that, I am going to hand it off to Andrea.
All right, thank you. Thank you, David. All right, so let's jump into the presentation now. Well, let's start with a quick reminder of what limit states should be checked in beams based on AISE, right? We have the flexural limit states like yielding, local buckling, lateral torsional buckling, tension flange rupture, right? We also have the limit states for shear. For instance, in this case, a shear buckling issue in a deep girder beam, right? And then for serviceability, we have the deflection and vibration checks as well, right? So all these limit states are covered by AISE formulae. And these code checks are also normally included within other software applications like structural applications, where they can easily get results from the analysis and then code check those beams using the AISE formulas. So like SAP 2000, ETABS, StatPro, all of those. So they cover almost all the requirements of structural steel designers, but there are some specific cases, and those are the ones that we will cover with IDEA StatiCa members. So let's talk about it. So let's now introduce IDEA StatiCa member. So this is an FEA application, and we use shell elements to analyze one member and its supports. Well, also you can bring the full frame as well, I mean the columns and the beam, but that is only analyzing, let's say, one portion of the full structure. So why we're analyzing only one member? Well, that is because we are not using 1D element or the beam theory. So we convert the full model into shell elements, including the connections from the analyzed member that we are, well, the focus member that we are analyzing in the application, and the connections to the support members and also all other related members. So imagine if we would like to model the full structure using shell elements. That will take a lot of time, right? So that is why we're focusing just in one portion of the structure. Then the workflow process is summarized in 3 steps within IDEA StatiCa member. The first analysis that we run is materially nonlinear analysis, okay? And there we can review stresses, strain on the model, and including the connections as well. And also, well, you can also review deflections order. Then we run a linear buckling analysis to verify if there is a buckling issue in your model, okay? And finally, if needed, you can run an advanced geometrically and materially nonlinear analysis with imperfections, right? That is only if needed. So what we get from IDEA member, what are the results that you get from it? So yeah, so basically it's how you can use dimensionate analysis and how can member be used in your design process. So the first thing is that you can model a huge range of member types, like non-regular beams with openings, with stiffeners, cold form sections, deep girder beams, built-up sections, those type of members that probably you can model it in your FEA software, in your structural FEA software, but there you are using 1D elements. So not all the effects on those members are captured, okay? So this is the great advantage of IDEA member. You can model whatever type of beam you have, or column, or detail, okay? Then you get accurate FEA analysis results using shell elements. So, well, all of those 3 points that I have here, you can also get it from other applications, right? But in this case, we are delivering the real internal forces considering the real stiffness on the model. That is because you are modeling the connections and realistic assumptions, like, for instance, stiffeners or openings, right? Then you get the real deformation on those members based on what you model, and you can get the stresses and the strain on the beams, all right? So you get accurate FEA analysis results. Then you can also run advanced geometrically and materially nonlinear analysis to capture effects like torsion, warping, and second order effects. So that is something that you cannot capture with beam theory or manual. Well, you can capture it with manual calculations, but it is hard to do it. Then the last point is that you can identify buckling issues on critical members, like they mentioned in this point over here. And you can use this factor to see if you need to either reinforce or run another type of analysis, like the geometrically nonlinear analysis. All right. So this is like a summary of what you can get, what you can do with member. Now let me show you what is the proposed process. First of all, you can use IDEA member in a standalone way. So you will open IDEA StatiCa, and then you click over the member icon, and then from there you can start from scratch. But the hard part of that is that you need to input all the results from your FEA, or you will need to input all the loads into that member, right? So this is why I like to show you member using other applications and using our links. So first of all, you'll need to run the analysis, of course, in your preferred application. I am putting here some of the applications that we have links, but if you didn't find your application, I recommend to go into our website so you can see if the application you're using, we can connect it to Checkbot. All right. Once well, you run the analysis, then you run the Checkbot interoperability. So I have done many webinars and videos that you can see on our website of how to bring your structure from these applications into Checkbot. So if you don't know, Checkbot is an application to translate all the information from other applications into the IDEA StatiCa world, let's say. And then once you're in Checkbot, you can open the joint or the nodes there, and then you can design your connections and run an analysis, code check those using the load combinations from your global structural analysis. finally, you can run an analysis on specific members that you know that those are critical, right? And because you already designed the connection, you can just click over the member and create a member item and then open member application. So here I have a summary, well, a video with this process. In this case, what I am doing here is, well, in this case, the structure is already on Checkbot, okay? And what I am doing here is merging these members over here. Why? Because probably from the application that you bring, well, all this geometry, probably that will be broke up into small pieces just because we have nodes over there. So you can merge like this member. In this case, we want to analyze this as a continuous member, right? So you select the member over there. Then we have a bottom at the top of the bar here, and you can select which members to merge. So you click over merge, and then you merge completely the beam, and then you start designing your connection. So you click over the cube, open that, and then IDEA StatiCa connection will be open. This is the regular process that I have shown you in other webinars. Feel free to look for those videos either in YouTube or our website. That's why I'm putting this in a speed. Well, I increase the speed of this portion, right? So then you add operations, or you use our connection library where you can save these connections. I mean, the proposed also workflow here is to design once this node, publish it into the connection library, and then reuse it in other nodes, all right? So as I said, you can run the analysis here, code check the connection, and have it ready for the member design. So this is the proposed workflow. All right. So once you have all the connections, let's move forward. Once we have everything here, right? You can see that all the nodes have something there. All right. So that means this beam is ready to be analyzed. Why? Because we have all the connections there. So for that, then you click over the member icon over here, select what member you want to analyze, then press enter, and then at the bottom of this list, you will have a members list. Then you can right click over that member, and then that will open IDEA StatiCa member. And you can see we bring everything, the connection that you designed before, and the loads from your global analysis. Okay. So once I jump into the live demonstration, I'll show you the application, well, the member application. All right. So let's jump into the live demonstration. Okay. So I'll open Checkbot. So here you can see that I just transfer one level of a full structure, right? This is because I just wanted to focus on one level. And probably you will say, okay, I just want to review this portion of the structure and some of the critical members that I have. So it is not necessary to transfer the full structure, okay? And that process, again, I already show it in some other webinars. Please visit our website. I have a lot of videos over there where you can review that process. So then let me just show you here. Look at these members. Those are all separated here, all right? So you'll need to come here to merge and merge those members there to create a continuous member. Then you also, well, if you're familiar with Checkbot, you can see that we have all the connections that are designed and analyzed. Those have a green check mark, okay? And then finally, we have the members over here. In this case, as you can see, I just select one member, okay? And all of the related members are like cut. This is because I just want to focus on one member, but if you want to focus in a frame here, like in this, there's 3 elements like this, and this, you can also do that. So when you're selecting here member and adding a new member, that is like activating the member application on those elements. So you click over here, and then you will need to select those 3 elements. All right, I'll escape this. There you go. So for instance, in this case, I select the 2 columns, okay? And if I will have the full structure here, I can select all the columns in that I mean in that joint or in that section, okay? All right, so again, different members can be assigned here, but let's open a very simple example. So this is a secondary beam, right? Or that means it is connected to a member that will have moments here. So this is a moment frame, all this over here. And this is just a secondary member, but look at this. It has like a 200 inches length, right? So it's a long member there. So I will right click and open this. Let's give it a sec, please. All right, so here you can turn off the members labels, so we don't have many things over here. So let's review what we have in this member application. So we always have the analyze member. So this is 19-bit member, okay? And this is the one we will run the analysis in. Then we have the related members. Here you can see those selected. Here you can see the supports. So that is the support at the end of this member. And then in the other end, we have a connection, right? So that is important for the stiffness of the analyzed member as well. So you can see all the related members over here. Then we have all the loads coming from the analysis, okay? And this is the hard part if you are starting from scratch. You will need to input all these loads on the analyzed member and the related members, okay? Then we have the connections. Those in IDEA member, if you say, okay, I just want to add the connections here inside, you can also do that. So you can click over, well, in this case, the joint or the number of the joint, and then you can edit connection. What is the problem of this? Is that you can just model the connection and not running an analysis. The IDEA StatiCa connection inside member, you cannot run analysis over here. So let me just show you so you can see what it's happening here. And even you can modify this design if you need it, but that cannot be calculated. You will need to close this, close member app, and then go back into Checkbot and open the IDEA StatiCa connection file from there, okay? To, let's say, modify something and rerun an analysis. So why we have this? Well, we don't want to combine results from IDEA connection in member and then IDEA connection in Checkbot. Okay, so that's why you cannot run the analysis. And then we have this operations. That's the last option here. So what are those operations? When you click over this member, you can add operations in the analyze member. So if you click over here, you can add openings, as I mentioned it before, stiffeners, longitudinal stiffeners, and a stiffening member, okay, cutoff plate, cutoff and stiffening member, weld, and lateral torsional restraint to, for instance, this member. So this is what I am referring when you can model whatever you need into this member. Okay, I'll show you later how to add an opening. First of all, I am going to show you results as it is. So I close that. So let's say you're okay with this. Let me delete the operation that I have here before. This is like analyzing the member as it was brought from your application. I will unselect some of the load combinations. I'll just select the worst case just for the time. And I'll select this S7 where well, I know that S7 is my serviceability load combination. Okay, so once you're okay with everything, then you click over calculate. Now we are just running the materially nonlinear analysis. Okay, so let's wait until it finishes. This will be fast because we just have to load effects. Once we do that, we can go into the check tab here. Okay, and here we have all these options to show. We can show the stresses here. Okay, all right, and then you can see the stresses in this area, in the area of the connection, but in the full member. Then you can also see the strain. We didn't have too much strain, so we didn't reach that plastic range of the material on this member. And the other interesting thing is that you can get the deflection. Okay, the total deflection over here. You can use this graphical plot to see what is the maximum deflection. Okay, but you can see that we have 1 inch, but over here in this red zone over here. Okay, so this is the deflection graphical plot. And then you can get the deflection in X direction, Y direction, and Z direction if you want to see that. Okay, so that is so useful in some cases. And the next thing is that you can see the internal forces. So let me show you that here, turning on the transparent view and internal forces. And then I'll select S8. So here you can see the internal forces, okay? And that common question that we have about where exactly is the hinge, that means zero moment. You can either use this internal forces to see that the real hinge in the shear tab is over here, right? A little bit before from the bolts position. Anyway, so you can see the internal forces, and then you can modify this graph over here to change it to MX, MY, MC, shear forces there, okay? And then BC as well, okay? So you can see everything there. All right. So that is what you can review when you're running this MNA. So now if you jump into the the buckling analysis, linear buckling analysis, you'll need to click over here, and then once you're here, you can click over calculate. Then it is starting the linear buckling analysis. So in this case, what we'll get is the 6 mode shapes and its buckling factor. So now we can see that into here, into this list, okay? And we'll see the different shapes over here. So you can click over the second shape. And that is when you start assessing if you will have a buckling issue. Remember that the linear buckling analysis, it is just only to predict if it's going to, if this member is going to have buckling issue. This is not a real deformation, right? This is only the second mode shape. And you can see the first one over here, the third. But you can see that we have low factors. okay? You can either select if you want to, let's say you don't want to do any reinforcement of this beam. You just want to see how this buckling is going to be reflected in the analysis or in the real deformation, okay? So what you will need to do there then is running a geometrical and materially nonlinear analysis. But that, before running that analysis, you will need to input either global imperfection or local imperfection. I'll talk about those later, but then you come here and modify this value over here, okay? So then once you input those, then you click over GMNA and then calculate, and then that will start the geometrical nonlinear analysis. All right. So that is basically what. Well, that is the process. I'll just hit calculate so you can see what are the results there. Remember that in IDEA StatiCa connection, we just run geometrical nonlinear analysis when we are using HSS members. In this case, we are running the geometrical nonlinear analysis for all the model. All right. So when you're there, you can see the stresses and strain and as well the deformation. Okay. So you can see here, and then the strain. So you'll have the same, let's say, FEA results for the geometrical and materially nonlinear analysis. All right, so that is the process. But then if you would like to assess, let's say you want to input the real, let's say, assumptions, because you analyze this and design this in your other application, and you got a successful analysis, because probably in the assumptions you did there is that you fixed this, you fixed the top flange, right? Because this will have probably a deck, so that will be fixing the deck, the top flange with, you will fix that with torsional and lateral restraint, okay? So that's why probably you didn't get those deformations or a bad design on this member. So you can come here, select the member, and add operations and add the real assumptions that you're using. So for instance, if you click over here, the lateral torsional restraint, you can select to which flange you're adding that operation, and you can also set that restraint if it's continuous or discrete. And if it's rigid, if the restraint on the torsional, if the torsional restraint will be rigid, or you can set an stiffness, okay? And then you can recalculate there, okay? So again, if you have an opening, you can add it here to assess the real behavior of the beam, okay? So probably you have some questions, but I can jump back when the questions, when we start reading the questions, and can show you here in the application. But now let's go back to the presentation to see or to understand the results that I show you. So, okay, from the first analysis, okay, you can see the stresses and strain to, let's say, to see if there is any hot spot, or to see if you need to reinforce a portion of the structure and you don't want those stresses like in these openings, right? So that can help you to spot those issues on the member. Then there in the stress and strain part, we also have this 5% limit on plastic strain, okay? If a portion of the beam has more than 5% of plastic strain, will tell you that that plate is failing. This is following the same the same procedure we have in IDEA StatiCa connection, all right? Then for the deflection, you can review the deformation of the serviceability load case, and then you can check against deflection limits. That's how you, let's say, review results in this first analysis. Then, when we are running the linear buckling analysis, as I show you, you will have 6 mode shapes for every load combination. You identify the critical factors. And how do you identify that? Well, you can use the limit recommended factors that we have, okay? And then if the factor is below the recommended value, you can use the geometrical nonlinear analysis to get an accurate analysis, including imperfections, okay? So these are the recommended limit factors for LRFD, okay? So you will need to use your engineering judgment to see if this is a global or local buckling issue, okay? So we have this factor or recommended limit factor of 12 for an steel grade of 36 and 9.16 for a steel of 50 kci, okay? So this is following the same, again, the same process of reviewing buckling analysis in IDEA StatiCa connection. This is similar because, well, we're talking about steel, right? But the only thing that you will need to review if this is a global or local issue, okay? But what if this factor is below? Again, you can run a geometrical and materially nonlinear analysis and add the initial imperfection within this table. And you can add the imperfections for each of the mode shapes, okay? So this is for, let's say, again, you don't want to reinforce, and then you want to reveal how the deformation will be in the analysis using this geometrically nonlinear analysis. Okay, so that is how it works. So we have this advanced analysis in IDEA StatiCa member. Normally, if you would like to run an analysis like that in a beam or an structure, you will need to use software like Abacus or ANSYS to run a geometrical nonlinear analysis, and we have it here in IDEA member. Is, well, very easy to use. All right. So now let's talk about what AISC says about advanced analysis. So the portion that I am referring to is on Appendix 1, okay? And that appendix, let me just do a zoom over here. That appendix is divided by the general requirements, okay? And then the second and the third is designed by elastic analysis and inelastic analysis. The one that I am referring is 1.3, designed by inelastic analysis, okay? And here you can see the general requirements and what the inelastic analysis shall take into account. So I did that list over here, and this is what AISC is asking. So having the flexural, shear, and axial and torsional member deformations, all right, and all in the analysis included, considering the second order effects, geometric imperfections, and stiffness reductions due to inelasticity, and then uncertainty in system, member, and connection strength and stiffness. So how IDEA is covering that part, or IDEA StatiCa member, let's say. So the first point is covered by the use of geometrical and material nonlinear analysis. The same for the second requirement, okay? Then the geometrical imperfections, you can set those by using buckling mode shape, and then you can input those values over there. So in this case is asking you to consider the residual stresses. In IDEA StatiCa, it's not possible to set residual stress in the member. However, you can model those by reduction the elastic modulus. Okay, so that is allowed by AISE, so you can go into IDEA StatiCa member and reduce the value of elastic modulus. Okay. And finally, the last point is covered by the use of geometrical imperfections and stiffness reduction. All right. So sometimes it is hard to learn about this initial imperfections. We have like global and local imperfections, right? In AISC, we have a portion where they recommend to add the local imperfection by L divided by 1000, and then the global, it's the out of plumbus equal to height of the level divided by 500. So you can combine those in the most shapes, but you will need to, because this is the L divided by 1000 is referred to the local imperfection, and this one is to the global one. Okay. So in some of the softwares, you can add the global imperfection. Okay, so you will get the results with that global imperfection, but the global, you will need to input that value in IDEA StatiCa member when you are running that geometrical nonlinear analysis. Okay, and well, as from the last slide, here, this is what we are recommending, and also reducing the modulus of elasticity. Okay. So this is what you will need to do for those geometrical imperfections in IDEA member. So I gathered these 3 papers where these imperfections are, let's say, described and used in finite element software to do this design by inelastic analysis. So if you're interested in those, I put the links in the PDF that I shared in the handout PDF that we post here, and you will have access to the PDF also from the website. So I'll put these links over there, and I recommend that you read about that, because I mean, in the AISC code we have those like recommendations like this, but they are not very specific, right? So I recommend reading how to input those geometrical imperfections, for instance, for call form steel members. So that can help you to guide you to know what to input into the geometrical imperfections in IDEA member. All right. And finally, I want to share that we have verifications for the member application, and we also are comparing our results against physical testing and comparing the results versus commercial finite element analysis like ANSYS, right? So everything is on Support Center. And talking about Support Center, we have also a theoretical background there where we are explaining basically what I explained it in just 40 minutes, right? You can read about it, and well, let us know if you have questions, all right? So.
Thanks, Andrea. Do you want me to take it over?
Yeah. Go ahead.
Awesome. We do not have a whole lot of questions for now, but I'm sure more questions will be coming through as I speak. So the first question was about the call form sections, and someone was just asking if we could do built-up members in the member application, also for call form, like box headers. And so yes, the section library is the same as in the connection module, so you can use the custom shape builder and basically create any kind of connection you want in the member application as well. When you merge I don't think you need to demonstrate it.
Okay.
When you merge the beam member, the forces and the moments that were imported by the checkbot to the beam will not be different and should be recalculated. Is that correct? So merging the member.
Yeah. That won't change, like let's say the analysis results.
Correct.
Yeah.
And a question that just came in regarding the function of imperfection amplitude. Do you mind re-explaining what this is about?
Yeah, so that is basically what we are doing behind the scenes, is that we are using that factor to multiply the mode shape. So that is very technical thing about the software, but that is how, I mean, I can send you information if you put your email, but that is basically what you do when you're using a finite element analysis software, and then you use a linear Boolean analysis, and you use that factor to amplify the effect in the results. So that's basically what it is. I highly recommend to go to those papers that I show you, so it is better explained there from the technical point of view. Okay.
Okay. Another question about the integration that we have with third-party software. Is it possible to adjust a load pulled from the model? So, for example, a weak axis load on a wide flange member, could it be adjusted to apply only to the flange?
Yeah, let me see if we, yeah, we can modify that, because here you can see that this is in the member axis, so you can move that either using, I mean, you can use the member axis option here and then having this eccentricity or adding this eccentricity of the load. So yeah, that is possible.
Excellent. And I am currently out of question.
All right. I mean, it's a new thing. So we encourage that you guys start testing the software. It's a very useful application for I mean, for instance, castelet beams, cold form sections, deep girders. So yeah, I believe then that's it, right?
Yeah, thank
you
you,
want to
Andrea.
talk about potentially next webinars, I guess?
Yeah.
Oh, we have just a question just now. Can you import from AD?
Probably Autodesk.
Yeah.
Or
I guess if you want to just take a advanced design.
I'm not sure about it.
Do you just want to show maybe the page that shows all the integrations that are available?
Yeah, let me bring that in here.
Advanced design is in there. To be honest, we don't have a lot. It is in there. We don't have a whole lot of users in the US of advanced design, so I don't believe any of us in the US team has used that link. But towards the bottom of the BIM integration page on the website, there will be a tutorial to link with advanced design. Do you mind quickly showing the website? Oh, yeah, there you go. Thank you.
There you go. So where is that? Supported integrations?
Yep, correct. It's going to be towards the bottom.
Here.
There you go.
Oh, but I went to the concrete, so that will be steel. There you go. Yep. Yeah, and it is only, I believe it's only linked with IDEA StatiCa connection. Anyway, I'll copy this link to the person who asked. All right.
And I know that's something that we're going to be looking at in the future, as far as increasing the number of BIM links to member as well. So. All right, so just quickly to just let you know about a couple of other webinars we have coming up. On August 30th, we will be doing a webinar in conjunction with some people at Ohio State University. They've done some verification studies for us related to AISC pre-qualified moment connections. So we'll be doing a presentation. They'll be giving a presentation on their verification studies and kind of what they found from the implementation within IDEA StatiCa. And then on September 27th, we'll be doing a presentation on our Detail app. Many of you probably don't know what the Detail app is. So that is one of the software that are part of our concrete solution. This is the one that is first been migrated over for the US codes, so ACI, Imperial units. And it's really meant for designing the D region, so discontinuous regions within concrete members. So that'd be beams, walls, haunches, openings. So those are the two things we have scheduled right now for the next 2 months. So hopefully you can attend. And we don't have any other questions. So I appreciate everybody taking the time. Definitely feel free to reach out to us with any further questions, or as you're kind of getting into Member, playing with it. Yeah, that's what we're here for. So with that, we will go ahead and end the presentation and the webinar. Thank you very much. Have a good day.